Welcome. We'll learn diffusion slash Brownian motion today. So let's get started. What is diffusion? And diffusion diffusion is the net slash total movement of a given particles It can be like water or ammonia. Of a given particles from a high concentration of those particles, a high concentration to a low concentration. In the given ensemble. So that is diffusion in general terms. It's also the same thing as Brownian motion. So this satisfies the continuity equation. So diffusion satisfies the continuity equation, which the continuity equation describes a volume of a given solution, say water, a volume in of a given solution inside our ensemble, that's going to be equal to before and after. So the same amount of water inside our volume, say our ensemble or volume here, it's going to be equal. So pretty much before and after, it's equal. So therefore, there's nothing changing. It's still the same amount. Kind of keep it a little simple here. Even though, and this will be good for like if you want to test out food coloring in water, because for the most part, whenever you put in food coloring inside water and watch food coloring, therefore diffuse outwards inside the water, the continuity equation will therefore apply to that specific example, because the same amount of food coloring is still going to be there before and after. If you try doing that at home, just kind of take a bowl of water, a ruler, and some food coloring and measure the growth of the food coloring in water. It's going to satisfy the continuity equation. Same amount of food coloring is still the same amount of food coloring 3 minutes before 3 minutes before the experiment versus 3 minutes after the experiment. So keeping that in mind, the diffusion constant of that ink in water, of that food coloring ink in water, that diffusion constant we'll call D. So we'll call this plus diffusion constant D, and this D will be smaller in gases than in liquids, because in gases, so in a gas, the molecules are going to be much further apart. So the distance between water molecule over here on the left and then to the water molecule here on the right are going to be much greater than in liquids, where therefore the distance between the two are going to be much smaller in liquids. So there'll be more collisions happening in liquids, and the more collisions you have, the greater the diffusion constant, the spread. So diffusion constant is the measure of the spread of, say, food coloring in water. So, which will be liquids, so they'll be much closer together, and there'll be more collisions happening, and that'll cause the individual molecules to spread out more rapidly because they're colliding into more water molecules as well as other ink molecules, food coloring ink molecules, which will greatly increase the spread or diffusion constant D in liquids. Rather, in gases, the diffusion constant will be much smaller because the distance between, say, water vapor and oxygen gas, or the distance between those two are going to be much greater, so there'll be a lot fewer collisions happening. So you'll have our, say, oxygen gas and water vapor are going to be at a much greater distance. Again, the distance will be can be greater than what's shown on the board here, but it'll be a much larger distance, and so it'll be fewer collisions, and so it won't. So therefore, the diffusion constant D will be much lower and so therefore, oxygen gas is not going to be able to spread out as quickly in the gas. But there is also another factor too that also controls this diffusion constant D, the spread of the particles in a given ensemble or system, and that will be temperature. So temperature can also determine how fast the average molecular speed, because we're looking at average, we're not looking at individual, so it's hard to tell individual motions of molecules, so we can only see the collective motions, the average of all of the molecules in our system or ensemble. And temperature does play a factor in determining how fast the average molecular speed is. So therefore, looking at temperature, if we were to solve the Maxwell-Boltzmann distribution function, we would get a simple equation of describes the kinetic theory of molecules, which will be this equation right here. This is where E, capital E here is the average kinetic energy of is just the average kinetic energy of the particles in our system. This curly V here is nu, the Greek letter nu, that represents how many degrees of freedom our particles have in our ensemble. Divided by 2 times Boltzmann's constant here times the temperature of our ensemble. So, and again, kinetic energy is equal to this, so we can determine. So if E is kinetic energy, we can therefore use the kinetic energy equation, 1/2 mass times the velocity squared, the average speed, average molecular speed. We can sub that in for E there. That's going to equal to our temperature here. So therefore, if I were to increase temperature, my kinetic energy will increase, and so therefore my average velocity of the molecules in our given ensemble will also increase. And vice versa, if I were to decrease the temperature, the average molecular speed will also decrease. There'll be less kinetic energy. And this is something like this is pretty much what we see whenever ice is forming. So whenever we compare water, H2O, at, say, 72 degrees Fahrenheit room temperature, and compare that to 20 degrees Fahrenheit, so that's below freezing. The 72 degrees Fahrenheit, the water is liquid, it's more fluid, it can move, while 20 degrees Fahrenheit is much colder and it's frozen in ice. And at that point, whenever it's at ice, the water molecules will only have vibrational motion. They can vibrate a little bit. They won't be able to move up and down, forwards, backwards, and left or right. So their degrees of freedom will be greatly reduced. So our degrees of freedom would therefore be 1 for ice. So they'll only be able to vibrate, while water at 72 degrees Fahrenheit will have, say, 5 degrees of freedom. They'll be able to move in our ensemble, either up and down, forwards, backwards, left or right, clockwise or counterclockwise, rotation, and then also vibrational motion as well. So temperature does play a factor in molecular speeds. And some examples of diffusion would be like Earth's atmosphere. So, like whenever you're watching the weather, wherever you're at, and they talk about high pressure systems and low pressure systems, and usually the low pressure systems are where things are more chaotic. So that's where your tornadoes and hurricanes or typhoons start to form, is at those low pressure systems. And again, it pretty much follows the same idea of diffusion or Brownian motion, in which you have a movement of air molecules in Earth's atmosphere, so nitrogen gas. So Earth is mostly made up of nitrogen gas. About 70% is nitrogen gas into, and the rest is made up of carbon dioxide, water vapor, and a bunch of other stuff as well. Methane gas as well as ozone. But usually it's what's mostly moving around is the nitrogen gas, the water vapor, and the carbon dioxide. And so it's going to be moving around in Earth's atmosphere, moving from a high concentration to a low concentration, so high pressure to low pressure. And again, whenever those different gases meet at a low pressure system where there's a lot less of them on Earth, that's whenever things get more chaotic, and therefore different temperatures, because say we have much warmer nitrogen gas and CO2 and water vapor from the south near the equator moving up to the northern hemisphere. And so that's going to be much warmer compared to those same gases coming from, say, the Arctic Circle down to the equator. They're going to be much colder, and so, but they all want to reach equilibrium because they want to fill in that low pressure spot, because again, that's what diffusion is. It's high concentration to low concentration. So that's going to, so those gases at different temperatures are therefore going to mix, and that's what's going to cause your tornadoes and hurricanes or typhoons, as well as cyclones. They're going to form at that low pressure spot, and because they're mixing together. And that's again where also thunderstorms happen as well. It's again at that low pressure because there's that mixing of temperatures, and that dramatic change in temperature is going to be very chaotic. And therefore cause the particles to diffuse and can form deadly storms. And again, this is all controlled by, and again, this temperature is controlled by Earth's heating from the sun. So when the Earth collects heat from the sun, it's going to say, we have our sun here, it's radiating heat on Earth's surface. That infrared heat from our sun is going to heat up Earth's surface, which will therefore heat up our particles near Earth's surface. They're going to rise up because again, warm air rises, hot air rises, and whenever it's up here at like above the stratosphere and into the mesosphere, it's going to be much colder there because there's hardly anything near the very edge of Earth's atmosphere, so it's going to be very cold. And so when it's very cold, it'll make those hot particles cooler, so they're going to want to move together, become more dense. The density of the air will become more dense. They'll fall back down to Earth's surface, warm up, and continue to create these convection cells. This rising and lowering of nitrogen gas, water vapor, and carbon dioxide, and etc. Just rising and falling, warming and cooling, because warm air is less dense than cold air. And this is also, again, very similar to what we see on the sun's surface. So near the photosphere region, you kind of see these. So near the So therefore, near the sun's surface, you kind of see that same convection cells near the photosphere. Call them kind of granules. They're they kind of look like what I've drawn right here, in which, again, they follow the same convection cells. This is the sun's inner core, or approaching the sun's inner core. This will be, say, the photosphere up top, which the photosphere is the light part of the sun. That's where light escapes the sun. So astronomers call it the photosphere, where light leaves. But kind of right below that, right around that photosphere region, we kind of see these convection cells. We see these granules over here, up here, and that's the convection cells bringing material like light to the surface of the sun, where therefore it is emitted. And that emission can be, again, is charged particles that will later form the solar wind, just kind of where radiation pressure is just pushing everything near the sun's core outwards, resisting the sun's own gravity, because they have a lot more energy to do so. They can escape the sun's gravity. So again, they're much smaller, and so again, it's kind of similar. There's a so the sun's inner core will be a high concentration of particles moving to the photosphere, where there's a low concentration of particles. So again, there's that same diffusion happening that is therefore driving how many photons are leaving the sun, and also driving, at least at the very basic level, driving the solar wind, bring charged particles up outwards where they start to build up, and near the magnetic field, near the sun's magnetic field lines, and eventually the magnetic field lines can't hold back the charged particles, and so they break apart. They break the sun's magnetic fields lines and shoot out in a burst of energy in one direction. And that's pretty much it for. So a lot of interesting things are happening with diffusion. Just if we were to just watch food coloring, drop food coloring in water, and kind of just measure the diameter of that food coloring for like 3 or 4 minutes, keep just recording the diameter every 15 seconds, so then we can therefore produce a table and a graph. We can therefore see that diffusion is trying to approach some equilibrium. It's moving from a high concentration point to a low concentration point. And so that's where it's therefore formed together. And I hope you enjoy learning about diffusion. If you have any questions, please ask.